Hello there, my name is Charles Msipa. Welcome to another presentation on functions of complex variables. Today we're going to look at the concept of what we call conjugate functions and the conjugate harmonic functions. Okay, let's say we're talking of conjugate and harmonic functions. First of all, let's recall that f of z, a function of complex variable, can be written as u of xy plus imaginary unit v of xy. That's the structure I just got. In this case, you can see that it's the usual rectangular structure of a complex number. Now, the functions u and the v, we're talking here about functions u of xy and the v of xy, which actually satisfy the Cauchy-Riemann equations. I'll write here in short C stroke R, the Cauchy-Riemann equations. Hoping you remember the Cauchy-Riemann equations. Say du delta u, delta x equals to delta v delta y and delta u delta y equals to minus delta v delta x. So what I was saying is that if I given a function, complex function in this form, and got u and v which satisfy the Cauchy-Riemann equations, then these functions are going to be called conjugate functions. In other words, we're saying that once v and the u are satisfying the Cauchy-Riemann equations, we call them conjugate functions. If in addition u and the v satisfy, if u and the v satisfy what we call Laplace equation, which is second derivative, partial derivative of u with respect to x plus second partial derivative of u with respect to y, the sum of the two gives us 0. Now, if u and v satisfy this equation, we will then say that u and v are harmonic. We will say u and v are harmonic. So, in the case that f is analytic, meaning it satisfies Cauchy-Riemann equations, then u and v, u of xy and v of xy are going to be called conjugate harmonic functions. I hope you note that here it is possible that the function u and v can be harmonic without f of z being analytic. But then if the functions are harmonic and f of z is analytic, meaning the Cauchy-Riemann equations are satisfied, then we'll call those functions conjugate harmonic functions. So what is interesting about this concept is the exercise we can do in relation to this concept. Let's say, for example, let's say we're given as for example, v, a function of xy, which is equals to 2xy plus 2y, and then we are required to find the conjugate function u. In this case here, we don't have u, so we must find this u in such a way that f of z, a complex function, would be equals to u x y plus I v x y, which were given. And now this example in particular, let's work it under this following condition, that f of z is analytic. So f of z is analytic. We must be able to translate what analytic means, and analytic throughout the plane. Now it's analytic throughout the complex plane, analytic throughout C, and we have that the value of f of z at 1 is actually equals to 4. Now, what do we have to solve such an exercise? If we know that f of z is analytic, we've got Cauchy-Riemann equations, and then we've got this condition. We'll see how we're going to use it. So now we are in search of u. So where do we start? Let's start this, let's say, solution. Now, initial step, we're given v. We shouldn't lose sight of that. We're given v of xy, which is 2xy plus 2y. Now, in this discussion, I would like you to closely observe how I'm using the theory, which we have already got, to answer our problem. In this case, our problem is to find v in such a way that our problem is to find u of xy in such a way that a function f of z given by this expression is an analytic function. So we must use that condition there, which is given as analytic. Then we'll see later how to use this condition. So our initial step, we will know that. Then analytic gives us Cauchy-Riemann equations. In this case, Cauchy-Riemann equation, the first one we have is that du delta u delta x equals to delta v delta y. I hope you've noted that I'm making an effort to avoid saying dv or du, because every time we're talking about dv, du, we'll be talking of an ordinary derivative of v, maybe with respect to x or with respect to y. but when we're talking about delta, we're talking about partial derivative. So please, I want you also to get used to that kind of language and use it appropriately. So when we're speaking about this thing, we actually have a shared understanding of what we're talking about. So now we know this by Cauchy-Riemann equations, which then says that this is equals to 2x plus 2 as a partial derivative of this v with respect to x. This is according to the Cauchy-Riemann equations. Then step number 2, which next step will basically be based on what we know about integration and differentiation. Now, if we know that this is a derivative and you are actually searching for u, then I hope you all understand that if you've got a derivative and this is a derivative with respect to y, we need this is a partial derivative of u with respect to x. So to get u, I hope you understand that we can recover u in terms of x by integrating this with respect to x. So we gave the 2x plus 2 dx. Because we're dealing with a function of two variables here, when I'm doing this, I'm writing an ordinary dx here for integration. But you must understand this somehow, that this is a kind of a partial integration. We're only integrating with respect to x. Then this is, we're integrating to x to actually recover a function of two variables, x, y. Then we'll get this as x squared using power rule there, then plus 2x. And because this is an indefinite integral, we must add a constant. I would like you to pause a bit here and think about what kind of a constant are you going to add here. A hint is that, remember, when you are having a function of two variables and you are doing partial differentiation, all the part of the expression of that function which does not depend on the variable which you are differentiating with respect to, all differentiate to 0. So then when you're going to add a constant here, you should incorporate that. And then how do you incorporate that? We then add here a constant, a function g of y. So I was sort of saying, to get this as a partial derivative of u with respect to y, or u being a function of x and y, there should have been part which depends on y and some constant, and all that when you are differentiated went to 0. So now when you are coming up with a constant here, you must come up with a constant which is actually a function of y. I hope that is clear. Now we've used one equation. In this case, I'm talking about the Cauchy-Riemann equations. Then we may now proceed to see how we can use the other equation. Then let's take here step number 4. Then what do we know about the other equation? That the partial derivative of v with respect to x is actually equal to partial derivative of u with respect to y. What is actually important here, which I never even emphasized before, is that this equation is actually saying these two derivatives are equal. They only differ by the sign, how it's plus or minus. So then, what we're actually given here, we're given v. If we're to differentiate with respect to x, we would need a minus sign to obtain, we would need a minus sign we multiply that by minus sign. So what we have to do now, we differentiate u, which we have got here, with respect to y, and you put a minus sign before that. What you're going to get, you're going to get 0 plus 0 plus g prime. And again there, we never use prime for partial derivatives, but you must think of why am I able to use prime here. Remember, this is a constant we recovered from the partial derivative of u with respect to x, and we say the part which only depended on y, now is a single variable, must be recovered as a constant function of y. So now here it makes sense to put prime for ordinary derivatives. This again is expressing the second Cauchy-Riemann equation. Then what we have here, we can now substitute dv dx and equate it to this. Now as we're saying, this is equals to dv dx. We differentiate here with respect to x, we get 2y. Then what you're actually saying here is that we can now say, therefore, minus g prime y is equals to 2y, which is the same as saying g prime is equal to minus 2y. So we can write this as g prime equals to minus 2y. So now we can see here that we have got a suggested form of u, the function we're looking for according to the question, and the only part which is missing is the expression of g. So now when we get here, we are actually got a way to move forward to get g. This is a derivative. Again, we know that from a derivative we can obtain the function by integrating. So integrating this, you can say now therefore g of y, I'll write this without using the integral sign, but knowing that we're integrating. Yes, then this will be minus y squared. Using power rule, that divided by 2, get minus y squared. Then you can say now plus a constant c, like would add with functions of single variables. So at this stage now, we can now say our u is of this form. U of xy is equals to x squared plus 2x plus g, which is minus y squared plus c. Rewriting this nicely, you can write this as x squared minus y squared plus 2x plus c. Now we have got c with an additional coefficient there. We've got u with an additional coefficient c. Now we can now start building up f of z as x squared minus y squared plus 2x plus c, that's our u, plus imaginary unit v, and the v was given as 2xy plus 2y. So we can write here 2xy plus 2y. Now, to get this exercise to its final form, we need now to reverse this process back from xy, from in terms of x and y, to in terms of z as a function of z. We've got a lot of things which we've seen before here. X squared minus xy and the I to xy. If we group that together, x squared minus y squared plus 2xy. We're grouping that from experience from what we've seen before. Then plus 2x plus imaginary unit 2y plus c. What we saw before is actually that this is z squared and this is 2z, because we can take out a common factor 2 here to get 2 brackets x plus imaginary unit times y. So now we see what we've got. We've got z squared plus 2z plus c. So now we've got our f of z, which according to what we've done is analytic because we went through the Cauchy-Riemann equations. But what we haven't used in this exercise is this condition says f of z at 1 is equal to 4. And actually that is what is going to give us, which gives us an idea that we can now obtain c. So taking f of z evaluated at z equals to 1, this will give us 1 squared plus 2 times 1 plus c, but this is said to be equals to 4. Now simplifying this, we can see that we get here 2 times 1, which is 2 plus 1 is 3, so we've got that 3 plus c is equals to 4, which you can then say therefore c is equals to 1. So under these conditions, we can now conclude that the actually required f of z, function of complex variables, is z squared plus 2z plus 1. And this is our answer to the problem. I hope the process is clear, and I hope you'll be able to go through it again and master how to do this type of exercise, because this is very, very important. As you can see, when we started given v, we were able to find u and end up with f of z. We could also do exactly the same thing given u and the target v until we get to f of z. Just quickly going through the exercise again, this is what happened. Sorry, this is where we started the example. Given v, we're looking for that. Then our initial step is to consider v. Then consider the equation, the Cauchy-Riemann equation, which says the derivative of this is equal to that. This is exactly where this is very important, because now we get it as a derivative of u respect to y, but at the same time, because of the equality of Cauchy-Riemann equations, this is also a derivative of u, which gives us an idea that having a derivative of u, you can integrate to recover u, which you get this way. And then you should be careful here that you just don't add any other c, but a c, a constant, which is a function of the other variable, because these are functions of two variables, x, y. Then, once you've done that, you proceed to the second Cauchy-Riemann equation, which also using it gets us to the fact that the partial derivative of v with respect to x is 2x, but that is also equal to minus the partial derivative of u with respect to y, which gives us this kind of an expression, which takes us to saying that gy prime is equal to 2y, which then will give us a way of getting this unknown constant here. Then again, we do it by means of integrating, and you get that. Then what follows is to reorganize your, build up your function f of z, and reorganize your expression in such a way that you end up with the expression of z in terms of z. What is important is actually to know these kind of manipulations in order to be able to push forward to get your final expression of f of z in terms of z instead of in terms of x and y. Otherwise, I think this example, and looking at examples given in your text, you can now be able to tackle this kind of a problem. For now, thank you for listening.